Okay, so I think the very important concepts that we learned in this session was the concept of random variables and how we can define the random variables, and the fact that how we can go from looking at the outcome of the random of our experiments, of our random experiments that lead to sample spaces. Remember, that's what we had in previous weeks. So we run some experiments. These random experiments lead to some outcomes that we put all of those possible outcomes in the sample spaces. Then from those, we can go ahead and extract different random variables. And we can then look at the possible values of those random variables and see what are the possible values and what is the probability that each one of them happens. For example, if I have my random experiment as, so flipping a coin 2 times, that's my random experiment. Okay, that's my experiment. Sample space. When I run this experiment, can you tell me what are the possible outcomes of these experiments that I can put them in my sample space? What are the possible outcomes?
Heads and tails.
Okay, you either see, okay, so you flip a coin 2 times, one after another. So let's say the first time you see head and the second time you see head as well. This is one possible outcome of that experiment, right?
Yeah.
What are the other possible outcomes?
Tails, tails, head, tails.
And tail head.
And tail head. Okay, so these are possible outcomes of these random experiments, and we put all these possible outcomes in the sample space. That's what we have learned in the past 2 weeks. Now I can look at these random experiments and I can define some random variables that can quantify the outcome of this experiment. So let's assume I defined a random variable, and I define my random variable like this: number of heads observed when you flip a coin 2 times. Okay, so I define this random variable as number of heads observed when you flip a coin 2 times. When you flip a coin 2 times is exactly the definition of my experiment that I defined here. So then, and also I'm going to show this random variable maybe with some notation. I'm going to show it with x, okay? So can you tell me for this random variable x that shows number of heads observed when you flip a coin 2 times, what are the possible values? What are the possible values for number of heads observed when you flip a coin 2 times?
0, 1, and 2.
Okay, so can you tell me when the 0 would happen?
When it's tails, tails.
When it's tail, tail, then I observe 0 head. Because here I'm looking at number of heads. So when it's tail, tail, the outcome number of heads is 0. When would I observe 1 head?
You have head to tail head.
Head, tail, head. I observe one head. And when would I observe 2 heads? Then it's head, right? I observe 2 heads. So if I define a random variable as number of heads observed when I flip a coin 2 times, what are the possible values for this random variable? What are the possible values?
0, 1, and 2.
0, 1, and 2. And okay, so these are the possible values for this random variable. So I look at one experiment, I look at possible outcomes of the experiment, and then we can define different random variables that can quantify the outcome of this experiment. Okay, I could say number of heads, I could say number of tails, I could say, I don't know, a number of times that at least one tail is observed and things like that. So I have different ways to define random variables on top of these experiments that we have defined. And these random variables basically are there to quantify the outcome of an experiment, a random experiment. Okay, so now I want to know the possible values of this random variable. The possible values are obviously 0, 1, and 2. I also want to know the probability associated with each one of them. What is the probability that the random variable takes value of 0? What is the probability that the random variable takes value of 1? What is the probability that the random variable takes value of 2? Okay, so I need to be able to calculate those as well. So what is the probability that the random variable gets value of 0? That happens only if this outcome is observed. What is the chance that when I flip a coin 2 times, I observe this outcome? Or let me ask you this question. Okay. When I flip a coin 2 times, can I say all these outcomes have the same chance of happening? Is that correct? Any one of them can happen. It's not that one of them has a higher chance than the other one. Is that correct?
No.
Why not?
Some of them has more chance than the other ones.
Which one of them has more chance?
The head, tail, and tail head.
Why do you think they have more chance? It's a fair coin. You flip it, you can see anything in the first flip, and you can see anything in the second flip as well. Why do you think head, tail, and tail head have a higher chance of happening than compared to tail, tail, or head, head? So basically, I can say any one of these outcomes, they have equal chance of happening. So any one of them has the chance of 1/4. When we flip a coin 2 times, there's 25% chance we observe head, head. There's 25% chance we observe tail, tail. There's 25% chance we observe head, tail, and there's 25% chance we observe tail, head. It's not that one of them has a higher chance of happening and one of them has a lower chance of happening. Yeah, think about it. When you flip a coin, a fair coin, and it's just any one of these outcomes have the same chance of happening. So if that's the case, then what is the chance that when I flip a coin 2 times, I observe tail, tail? What is the chance that this happens?
25%.
25%.
1/4, right? Then it is the chance of 1/4 tail, tail happen. If tail, tail happens, then the number of heads observed is 0. What is the chance that I observe head, tail, or tail, head?
1/2.
Which is basically 1/4 plus 1/4, because I say this happens or this happens. It's 1/4 plus 1/4, or. So that's 1/4 plus 1/4, which is 2/4 or 1/2. If that happens, if those two outcomes happen, then I observe 1 head. That's when the random variable 1 is observed. And what is the chance that I observe 2 heads?
1 over 4.
1 over 4.
1 over 4. And when that happens, then the random variable gets the value of 2 because I observed 2 heads. Okay? So then I came from an experiment that has 4 possible outcomes to a random variable that can get 3 possible values, 0 or 1 or 2, and I have the probability of each one of them. And thus, I have the probability mass function of this variable, this random variable. I know the possible values. So basically, I know the possible values that are 0, 1, 2, and I know the probabilities. And the notations to write it is either lowercase f, capital X at the subscript, x, which is probability of x equals to x. Or here I can say f of x 0, or probability that the random variable takes value of 0 is 1 over 4, f of x 1, or probability that the random variable takes value of 1 is 1 over 2, and f of x 2, or the probability that the random variable takes value of 2 is 1 over 4. So I know the possible values for this random variable 0, 1, 2. I know the probabilities of each one of these values happening. So I can say that I have a probability mass function, but can you tell me what are the 2 conditions I have to double check to make sure if it's a probability mass function? What are the 2 conditions? One of them is that f of x is greater than or equal to 0. That means the probability for each one of those x values is greater than or equal to 0. And the other one is that
sample space or equal to 1.
Yeah, the other one is that the sum of these probabilities is 1. And I have to check this to make sure that it's a probability mass function. So I know the possible values 0, 1, 2. I know the probability of each one of them here. Okay, is each probability greater than or equal to 0? Yes. The first condition holds. Do they add up to 1? When I sum them up, do they add up to 1?
Yes.
Yes, they add up to 1. So then this definitely holds the definition of a probability mass function for this random variable. If I have something like this, then I can say that I have the probability mass function of a random variable. I can tell you the possible values, and I can tell you the probability of each. Okay, so that was the probability mass function. And then you also learned the concept of the cumulative distribution function, which basically capital F x x. So that's probability that a random variable is less than or equal to the x value. So here, this is probability that my random variable is equal to this value. This is the probability that my random variable is less than this value. Whatever I'm going to put here is less than that value. So that's what I call as cumulative distribution function. And let's, for this probability mass function, let's define f of x for all possible values. So f of x 0 means probability that the random variable gets any value less than or equal to 0. Can you tell me what is that probability? Any value less than or equal to 0? There's nothing less than 0. It's just equal to 0. That's 1 over 4. F of x and then 1 is probability that random variable takes any value less than or equal to 1. What is that?
0 over 4?
1, 4 plus 1.
Exactly. So it's 0 plus 1, which is 1 over 4 plus 1 over 2, which is 3 over 4, and then f of x2 less than or equal to 2, which is probability of x equals to 0 plus probability of x equals to 1 plus probability of x equals to 2, and that's 1. So then if I have this as well, if for each one of the possible values 0, 1, and 2, I know exactly what is the value of these probabilities, which I know 1 over 4, 3 over 4, and 1. If I know this, then I also know what is the cumulative distribution function of that random variable x. Okay, and usually if you have the CDF, you can extract the PDF, probability distribution, probability mass function, PMF. And if you have PM probability mass function, you can also construct the cumulative distribution function. Let me give you an example. Okay, let's assume I have a jar, and in this jar there is one black ball. There are 4 balls, and one of them is a black ball. And I define the random experiment to be pick balls without replacement till I get to black ball. Okay, that's my experiment. Pick balls without replacement till I get to black ball. Okay, so I correct myself. My random experiment is pick balls without replacement till I get to the black ball. So, so these are possible outcomes. I pick balls without any replacement till I get to the black ball. Then I define the random variable as number of balls that I have to pick till I get to black ball. Okay, so my experiment is just picking the ball till I get to the black ball, and these are possible outcomes. But then my random variable is number of balls that I have to pick till I get to the black ball. Okay, and I define the random variable as x. Then can you tell me what are the possible values for x? Number of balls that I have to pick to get to the black ball. What are the possible values?
1, 2, 3, 4.
1 happens when the first ball is the black ball itself. So then possible values. 1. And in this scenario, then the possible value is 2, because then I have to pick 2 balls till I get to the black one. Then here I have to pick 3 balls till I get to the black one, and then in the last one I have to pick 4 balls till I finally get to the black one. So the possible values that these random variables can get are 1, 2, 3, 4. So then if you want, you can continue calculating the probabilities till you find the probability that any one of these four numbers happens. So what is the so if I want to calculate the probability mass function, I have to find f of x1, f of x2, f of x2, f of x3, and f of x4. So let's say I'm going to calculate f of x1. F of x1 means the probability that random variable takes value of 1, which means this scenario happens. You pick a ball, and that first ball is the black ball. What is the chance that it happens? You pick a ball from a jar that has 4 balls, one of them is black, and what is the chance that it happens? The first ball that you pick is a black ball.
1 out of 4.
4.
Can you repeat one more time, sorry?
1 over 4.
1 over 4, exactly. So 1 over 4 is the probability that the first ball that we pick happens to just be the black ball. All of the balls have the same chance to be the one that we pick. And what is the chance that it's the black ball? 1 over 4. Okay. Now, f of x 2, or the probability of x equals to 2. When would that happen? When the first ball that we pick is a white ball, and then the second one is a black ball. And remember, we do this without replacement. So I have 4 balls, and 3 of them are white, and the first one is black, and then one of them is black. What is the chance that the first one is a white ball? I pick a ball from this ball. What is the chance that it's white? Do you hear me, guys?
3 over 4.
3 over 4. 3 out of these balls are white. So 3 over 4 are white. And then it's without replacement. So let's assume I pick this one and I remove it from the ball. So I want the first ball to be white here, and I want the second ball to be black. And what is the chance that the second one is black? Given the fact that one ball is removed, this one is removed.
1 over 3.
1 over 3. So there are 3 balls left, 2 white, 1 black. What is the chance that then I pick 1? What is the chance that it's black? 1 over 3. So then that's the probability that there are that I need to take 2 balls till I finally get to the black one. With the same logic, we calculate f of x3. The probability that x equals to 3. I need to pick 3 balls till I get to the black one. So again, this is your ball. 1 white, 3 white, 1 black. And I want to calculate probability that x is equals to 3. X is 3 is this one. The first one is white, the second one is white, the last one is black. So, okay, what is the probability that the first ball is white? Three over 4, right? You pick one ball from this ball. What is the chance that is, what is the chance that is white? It's 3 over 4, right? You pick one from this ball. What is the chance that is white? 3 over 4. Then, and it's without replacement. Let's assume this is the one that we pick without replacement. This is out of the ball. And we pick another ball. What is the chance that that one is white too?
2 over 3.
2 over 3. Let's assume that's the one we pick. It's out of the ball too. And we pick another one. What is the chance that it's black?
1/2.
It's 1 over 2. So that's 1 over 4 as well. And finally, oops. what is the chance that x is 4, which means out of these balls that are here, what is the chance that I need to pick 4 balls till I finally get to the black one? Which means, as you can see here, the first one is white, the second one is white, the third one is white, the last one is black. What is the chance that the first one is white? 3 out of 4. Let's assume this one is out. What is the chance that the second one is white as well? 2 out of 3. Let's assume this one is out as well. What is the chance that the third one is white as well? Out of these 2, what is the chance that is white? 1 over 2. This is out. What is the chance that the last one is black? For sure, the last one is black. That's 1 over 4 as well. So then this would be the probability of observing each one of these possible values. So I have a random variable. I know the possible values of that random variable. I calculate the probability mass function, the probability of associated with each one of them. I want to know if it's a probability mass function or not. I have to check 2 conditions. First, each one of them should be greater than or equal to 0, which is the case here. And then their sum should be 1, which is the case here as well. So f of x0 plus f of x1 plus, 1, 2, 3, 4. Their sum is 1 as well. So what we define here is a valid, correct probability mass function. And then I can also ask you that about a cumulative distribution function. So I can ask you f of x 3, for example, which is what is the probability that the value of this random variable, which is number of balls till we get to a black ball, is less than or equal to 3. What is the probability that it happens? So it happens if x is 1, or if x is 2, or if x is 3. So in these scenarios, x get a value which is less than or equal to 3. So we have to add those 3 probabilities. And we just calculated here that each one of them is basically 1 over 4. So basically it's 1 over 4 plus 1 over 4 plus 1 over 4 is 3 over 4. So you can calculate the cumulative distribution function, or CDF, for each for any possible value of this random variable. Okay. Any questions so far, guys? Okay. Let's look at this one. Let's assume I run an experiment, and these are the outcomes of the experiment. A, B, C, D. Okay? And so these are the outcomes of the experiment. And I'm going to define a random variable. I'm just going to define the random variable to get value of 0 when A happens or E happens, to get value of 2 when B happens, and to get value of 3 when C happens or D happens. Okay, so I run an experiment. These are 5 possible outcomes of that experiment. Okay, let's assume all these outcomes are equally possible to happen. If that's the case, then what is the probability that A happens? When we run the experiment, what is the chance that we observe A as an outcome?
1/5?
1/5, because I just said all these outcomes are equally possible to happen. When we run the experiment, any one of them can happen. Any one of them can be observed. If all of them are equally possible to happen and there are 5 of them, then if each one of them has the chance of 1/5. 1/5. Okay, so these are basically the probability for these outcomes. 1/5, 1/5, 1/5, 1/5, and 1/5. Okay. Then I define the random variable to get these possible values. And now I want you to tell me, first of all, what are the possible values for random variable I'm going to call it x. What are the possible values for random variable x? What are those possible values? Zero, 2, and 3, right? This random variable can get these possible values, 0, 2, and 3. Then I'm asking you, okay, what is the probability that I observe value of 0?
Two over 5?
2/5, because we observe 0 when A happens or E happens. Then the probability of random variable getting the value of 0 is when A happens or E happens, and each one of them has 1/5 chance of happening. So we observe 0 with a chance of 2/5. How about probability of 2?
1/5?
When do we observe 2? Only in this scenario, when B happens. And that's with chance of 1/5. And when I observe 3, that's when C happens or D happens, and that's 2/5 as well. Okay. So that's probability mass function of this random variable. When we look at the probabilities, we know the possible values 0, 2, 3. We know the probability each one of them, they are greater than or equal to 0, and the sum of them equals to 1. So it has all the characteristics of a probability mass function. If I had told you that these outcomes do not have the same chance of happening. Let's assume this was not given to you. They do not have the same chance of happening. I would actually give you their chance of happening. So I would have given you, I would say, okay, A has the probability of 0.1 of happening. B has the probability of 0.2. C has the probability of 0.25. D has the probability of 0.3. And E has the probability of 0.15. Let me just make sure I get the numbers correctly. Okay. So they do not have the same chance of happening, so forget about this part. I give you the probability of each one of them happening separately. And then still, I define the random variables to get the value of 0 when A or E happens, to get the value of 2 when B happens, and to get the value of 3 when C and D happens. So I still define it that way. Still, the possible values of this random variable are 0, 1, 2. And still, I want to identify the probability mass function to find the probability that the random variable gets value of 0 or 2 or 3. Then how would I change this? So probability that the random variable gets the value of 0, what would be the probability then? Instead of 2 over 5, what should I put?
25%. 45.
Is this when the random variable gets A, or the outcome is E, these two, then the random variable is 0, and that happens with probability of 0.25. Okay, I'm going to write it here. Okay. And how about 2? When would the random variable get value of 2? What is the probability that the random variable get 2?
0.2.
It's here. When I observe B, which happens with probability of 0.2. And when would the random variable get value of 3? When C or D happens, and that happens with probability of 0.55. When C happens or when D happens, and we add, right? Or we always add the probabilities here. And that's 0.55. And let me see, do they add up to? Yes, they add up. So now again, each one of these probabilities is greater than or equal to 0, and they add up to 1. So that's a probability mass function as well. So as long as you know the outcomes of an experiment, you know the outcomes, and you know the probabilities of these outcomes, then all you have to do is to find out what is the definition of the random variable. Obviously, for each set of outcomes we have had, so we can have so many random variables defined, depending on how we want to define. Carefully think about the definition of the random variable. Find out possible values of the random variable. I put RV just for random variable. And then find the probability of each value. And then at the end, check if it is a valid probability mass function. So that's all you need to do. There's nothing tricky about it, nothing complicated. Just read the experiment properly, correctly, read the definition of the random variable carefully, find the possible values of the random variable, and at the end, find the probability of those possible values, and at the end, check if that's a valid probability as well.